So today we enter into the final part of our third unit where we're looking at a development of a semi-quantitative theory of quantum mechanics, pulling together all of our experimental information into one key hypothesis, which in the next unit, which we will be starting soon, we will then use to build up a truly formal and exact quantum theory. But for now, we'll be looking at this final topic, which is very important for us to build up that intuition that we need in order to construct such a formal theory. And that is the fact that mechanical systems, such as the ones we've been studying, such as atoms, exhibit this interesting behavior of having certain discrete energy levels that are allowed to them, whereas arbitrary values of energy we actually never see. Now, this phenomena can be described by a procedure, a semi-quantitative procedure known as Bohr-Sommerfeld, or as I like to abbreviate it quickly, BS, quantization. Now, just a quick review of the salient points from last time that we will be building upon as we get into this issue of the discrete energy levels. Excuse me. You'll remember that previously we were applying the Heisenberg uncertainty principle to the hydrogen atom. And we found a very nice series of results. We began, as you always do, of course, in a quantum analysis, with the Hamiltonian for our system, which, because this is a mechanical system without a magnetic field, is numerically equal, actually, to the total energy of the system. We then performed a Heisenberg analysis on this to try to determine what the least energy we could expect on average would be. And we found that that minimum would be obtained. And this is then what we expect a system to settle down into after it's been left alone for a while to radiate off any excess energy. We found that it should assume a certain ideal size, which we computed, and here it is in terms of the corresponding fundamental constants, and the numerical value turned out to be just actually the size of the hydrogen atom. The minimum energy we then evaluated. It turned out we learned that the virial theorem actually came about from our Heisenberg analysis as minus 1/2 of this kinetic confinement energy cost, and that, or actually minus the kinetic energy is what the energy turns out to be, and that is this confinement energy cost. If we insert then delta R star in, we can evaluate the resulting expression in terms of the fundamental constants. And again, we get a beautiful agreement with experiment, somewhat fortuitous because this Heisenberg analysis is just order of magnitude level at this point. But nonetheless, we ended up, we lucked out and got the exact ground state energy, the known expected energy for the hydrogen atom. So that was really quite a success in terms of our first really applying the concepts from the de Broglie hypothesis to a more complex system, such as the atom. Now, the next thing we noticed was, we commented on, that if you now compare our prediction to the actual experimental observations, there's a puzzling mystery. So a mystery comes in here. And the claim that I made, and we will back it up now with experimental evidence momentarily, but was that when you carried out measurements of the energy for actual hydrogen atom systems, if you prepare them extremely carefully, letting them, wait around until they can get to their lowest energy state, and you measure their energies, we in fact find a distribution which is centered pleasingly, right, on what we predicted the average minimum energy would be when things settled down. But what was perhaps surprising is the fact that we always get exactly the same energy, not a distribution. For the Heisenberg analysis, we should expect a distribution typically because our momentum, as we know, has some spread in it, and so therefore this kinetic energy would have a spread. The potential energy also, because the positions have a spread in them, you would think that this potential energy would also have a spread in its values. And if you add together two random variables, each of which have a spread to them, generally the result that you get also will have a range of values. But evidently what is happening here is that whenever the kinetic energy is a little extra high, the potential energy must be correspondingly a little extra low, and vice versa, just so that when they add together, they always give this precise single constant value. that implies that in this system there must be some kind of strong correlation between our random variables. These r's and these p's must be big and small exactly correspondingly to reproduce this behavior. And this is just something that we are not prepared to address with this Heisenberg simple statistical analysis. We will need to introduce something new in order to explain it. Now, there's actually a little more to explain, because if we went on then and thought about the energies that we would measure for less carefully prepared systems, I claim something further. You might originally expect that, well, if they're less carefully prepared, then maybe this thing spreads out in energy kind of like I might have expected intuitively from the beginning, but that's not what happens. The energy values definitely spread out more and go to higher values of energy, because now these things are not all down in their lowest energy configuration. But the distribution of energies we get is very interesting. Once again, we don't get a broadening of this lower peak, it just stays just as sharp. What reflects the fact these are not all in their lowest energy states is that we now measure certain other energies, but we measure those also with very sharply peaked and well-defined values. And those values actually begin to crunch together, and they come closer and closer, and they finally reach an accumulation point. And there's a whole infinite array of these energies. So there's a lot we need to explain here, and in particular the fact that we have these very discrete energy values. There are not, you will notice, ever observations of hydrogen atoms with these kind of in-between energies. It's always just at these very discrete values. And this then is what we hope to explain today.